So, hi everyone, and yeah, for this talk, I will be discussing antenna topology optimization, and this is a nice new topic which has a lot of potential and a lot of depth to it. But I will try my best to explain to you some of the principles. But before I get started with the talk, I think it's actually quite appropriate to watch the following brief interview, if you will, of one of the founders of modern topology optimization. So let's take a look at that.
As a researcher who has been one of the inventors of topology optimization, I've been in that field for 25 years. And in the beginning, people were sort of laughing a little bit and saying, hey, you came up with this fantastic structure there, but nobody knows how to manufacture it. So what are you going to do there? And I said, well, let's see, with time, this will come. And so it has sort of steadily been increasing this field all the time here for 25 years. But now recently, in the last few years, it has really increased the speed of development with additive manufacturing and combining it with topology optimization. So for me, it's really fantastic to see how many industries that are using it. So essentially, additive manufacturing offers ultimate freedom for manufacturing, but they don't know how to come up with these optimal parts. And on the other hand, topology optimization uses this ultimate freedom to come up with parts that are optimized for specific load cases and extreme situations. And so topology optimization provides the designs to additive manufacturing, and additive manufacturing makes it possible to realize the designs coming from topology optimization. So that is an ideal marriage. So it's an interesting research area that still has so many possibilities and so many open ends. So lots of interesting research and development to be done there. And certainly the last sentence has not been said in that aspect yet.
So as you can see, this is quite an exciting topic that have been around in structural mechanics for a while, and it's really proven technology, even branching out into other physics like fluid dynamics and photonics. However, when it comes to electromagnetics, and specifically on the high frequency side of things, and as we're talking about antenna design today, I would say it's something that has not yet taken off. And so today I would like to introduce to you the topology optimizer we have available with the new release of CST Studio Suite 2024. As it is a new topic for antenna engineers, including myself, the essence of what I will present here is still fairly research and or very much research oriented, and I will be showing multiple test vehicles and examples that we have successfully done so far. But my hope is really that after this talk today, at least you will be inspired to try it out for yourself and really try and push sort of the boundaries of conceptual design for antennas. Now, we need to classify first perhaps the different optimization methods. Specifically, what we have available within the portfolio of SIMULIA is the parametric methods, which was just discussed in the previous presentation. In this case, I'm referring to iSight, or which is basically the standalone product, where on the platform you have the applications, process composer and result analytics based on this functionality, which is doing things like response surface method calculations, design of experiments. You're able to do Monte Carlo analysis, uncertainty analysis, all these different things to automate also the process of simulation and optimization. But it's all parametrically focused. On the left-hand side, then you have the non-parametric methods, which is provided by SIMULIA's tool called Tosca, also available on the 3D Experience platform through different roles available there. But I will be talking about the standalone version today, and it can cover different things like structural topology, structural shape, fluid topology, sizing, and even beading. So topics that are well suited for structural mechanics. And then of course there can be also a combination of both these groups. Now, what we are supporting in CST or with CST Studio Suite is specifically topology optimization, which we'll discuss today, and also shape optimization. So let me maybe first just introduce these non-parametric strategies to you. So on the left-hand side, you see just sort of a simple depiction of topology optimization. And basically, the idea is that we're trying to find well, the purpose is really to find some type of function from a black box. We can call it that. So basically, you have a design space depicted here by the green boundary, which can be either a sheet or a volume. And the idea is that after optimization, the mesh elements will consist of either the original material or the specified material for the filling. On the right-hand side, then we have shape optimization, which has the purpose of really starting from a design, starting from something that already has some performance, and you want to achieve really high performance. You want to squeeze out the last bit that you can. And the design space there would be then some surface area. This can also be a volume, just the surface of a volume. And the idea is that after optimization, mesh nodes are moved on this space and to really form this new shape. However, the focus of this talk today, specifically for our antenna applications, is topology optimization. I will circle back to shape optimization, and just a note on that as well. Tomorrow, during the filter and components day, we will have a session or a talk on shape optimization as well, and I'll touch a bit on antennas there as well. Anyway, so let's step to the next slide, which is just showing sort of an overview of our high frequency solvers. I'm not going to go into any details here. You have seen this in an earlier talk, the different solvers we have available. Now, for non-parametric optimization, we support the frequency domain solver with model order reduction, as well as the eigenmode solver with general lossy, so meaning that it can also take loading effects into account. But eigenmode solver is a bit more tricky when it comes to topology optimization, well suited for shaping. But we're not going to focus on this because we're going to focus on driven problems today, and specifically scattering problems for antennas or in terms of antennas. So let's talk about some antenna concepts. Let's start with just some conceptual things. So let's say you have a device here. It's specifically a camera with a transceiver on it, and it's supposed to upload really large files very quickly to the cloud. Of course, you need connectivity then, and well, this product is already close to production, and they need connectivity module. There's just a small space allocated within this product for the connection for the antenna, for the radiator itself. And so the question is what to actually put in there. So there will be this ABS plastic cover. So why not just print on the back of this cover? Okay, so you can see the plastic cover there. Yeah, can we explore this design space and see if something is appropriate? Some topology is appropriate. And what we do is, so you see this green space then on the back of this cover, which is not connecting with the device itself electrically or conductively. And you can see the coax connector placed in on the edge there of the design space. And the point is, this is just sort of the seeding point for this problem. It can be placed at any point, and you will get a different topology out. And so the purpose then, or the motivation is then, can we get radiating efficiency, or can we get radiation efficiently over the spectrum from 3.4 to 3.8 gigahertz, right? So here you can see then the topology that's starting to optimize, and the red colors are the dark red is really indicating then a good conductor, and you can see the blue section is just falling away, which is then vacuum in this case. And we are maximizing radiated power, which you can see the objective function in the top graph, and it quickly, after a few iterations, it's already getting very high. And of course, the input power is in CST Studio Suite is typically 0.5 watt, which means it's sort of getting close to that, reaching sort of a level of probably 90%. We'll look at the numbers in a second. You can also see at the same time the reflection coefficient just dropping below minus 15 dB in this particular case. And with that, you have this new interesting looking topology, and you can just go and verify then the results even with another solver to determine the radiated power efficiency and specifically then the input match, which you can see it's actually, you get a broader band, but of course your efficiency will degrade a bit. Now, another simple example, talking about integrated antennas, PFA antennas have been used for a long time, and they have good properties for multi-band, having a multi-band response. So the question is, can we take this, just the sheet in the same footprint, and could we achieve something similar or perhaps even better? And so what we do is we try and optimize or maximize the radiated power at 900 megahertz and at 1800 megahertz, simultaneously also constraining the reflection coefficient in both these bands. And you can see the topology just coming together. You see that inductive part also next to the feeding point coming together, or sort of still shorting out to the backplate there, which is also necessary for the lower band. And you can see then the radiated power again, 1800 megahertz and 900 megahertz going up. And the thing is, I mean, you need to verify these results again because, and I'll explain this in a second, but basically you want to specify some threshold for the densities. These intermediate densities are going from vacuum to the conductor to cut something out, to get some ISO cut, we refer to it, to extract the specific topology. And this threshold can also vary, and I'll talk about that in a moment. You can see then on the left-hand side also the input match and the radiated power at the bottom. So not too bad, but it is shifted. If you've noticed, the objectives were at 900 and 1800, so it's slightly shifted. And the reason for that is that we are actually working with intermediate densities, which can be observed here from the connectivity, basically going, if you look at the color ramp there, going from close to 0, which is essentially my vacuum or my air, to a very high value for a good conductor. In this case, I think it was copper or something. The result is that everything in between is essentially posing dissipated losses to the signals, right? Now, let me try to explain a bit why we need these. So with the topology optimization, the original integer problem is basically relaxed here and allowing then a continuous and intermediate sort of design variables. So these so-called intermediate densities then allows for a mathematical programming approach, basically, using joint sensitivities. So every element essentially is sensitive to some degree to my objective function or my constraint. And this joint sensitivity approach has a very good track record for efficiently optimizing large problems. So we're talking about being able to address thousands to even millions of design variables in just a few optimization iterations. Okay, so that's some context for why we use these density distributions. Now, here is a simple illustration of how efficient this is. We have a short printed monopole where the parasitic elements are used to obtain a good input match at 2.4 gigahertz, because of course, you know, when it gets so short, the radiated resistance is getting much lower, and so it's tough to match this. And yeah, so you can just see the topology coming together here, and you can see those intermediate densities falling out and just the red sort of topology remaining. And again, this is where you would do an ISO cut at some value. The default is 0.5 essentially, and then you get the picture on the left bottom corner. Now let's so in this case it took just 28 iterations to do this gradient-based optimization with a fairly dense mesh as well. So on the right-hand side, then I would like to you know, show this against a binary optimization approach, which is maybe more familiar to many people, where you basically have the cells going from on to an off state in terms of the material properties. So you can see there the square shapes being either just empty or with metal. Now, in this case, we have the same conditions for getting this element to radiate, to have a good match, to have some radiated power, but it requires 400 and almost 90 iterations for this optimization. Now, it is probably slightly unfair comparison, as the connectivity of these rectangular shapes can be less desirable maybe for conductors. But if you increase the number of elements, I mean, you can change the shaping, but you will probably have to increase the number of elements. The point is your number of optimization iterations will quickly start blowing up, and this poses also a problem then perhaps for efficient optimization. Okay, so enough on that. Let's go to the next topic, which is just electrically small antenna. So an antenna is considered electrically small when it can be encapsulated by a sphere with a circumference of, let's say, smaller than half a wavelength. And so this is the typical Ka factor for those of you familiar with electrically small antennas. And so here you can see just a folded spherical wire helix monopole that's available in Antenna Magus. You can see the reference for the literature it's based on at the bottom there. The point is, when the wavelength gets very short, the input resistance becomes very low, and of course, it's no longer efficient radiator, and it's no longer matched to 50 ohm, right? So we want to try and see if we can get something out of a design space that is within this range. So we make use of a hemisphere over an infinite ground plane, just a sheet suspended above ground. Of course, we make use of our knowledge of this design that I just showed you, and we place one coax port and 3 shorted pins. And these pins are basically just, again, seeding the design space to run in a certain direction, or to try and get a good topology in the end. So not being completely black box. And then in addition, we also use a type of perturbation density distribution. So we don't start from a uniform density distribution, but actually it's sort of perturbed, as you'll see when I show you this picture there. And you can then see when the optimization starts, these traces starts forming. And the objective is then to get maximum radiation at about 300 megahertz. And you can just see the shape coming together. Yeah, so if we look at the performance then, and we verify the results, and you can see the topology on the right-hand side then, we achieve about 6% fractional bandwidth, which is actually not too bad, because if you go and calculate the fundamental limit for such a size, you're talking about less than 10% fractional bandwidth. Yeah, but without going into too much details, the point is we do get some good results, and as expected also we get a good vertical polarization over this ground plane with a small horizontal component. And again, look at the convergence curve on the left-hand side corner. You know, just about 80 iterations, and the power, the radiated power is maximized in this case. So we've talked a lot about the sheet sort of antennas, optimizing sheets. Let's talk about the volumetric antenna. So as I described before, it's also possible to have a volume or a volumetric mesh and try and find the topology there. So similar example than what we had before. This time we're filling that whole space just with metal and then trying to find the topology within this. You can see the topology that sort of comes out. Again, it's dependent on where you're feeding it, how you're feeding it. So I'm not going to go into the details of those. I'd rather move on to this interesting example as well, which is dielectric resonator antennas. Now, of course, you can do characteristic mode analysis on this stuff, or you can just take a simple example from Antenna Magus and see if you can even improve it. So this is just the simplest form, with a rectangular resonator and the pin fed through an infinite ground plate and with the dielectric constant of 20. And so the reflection coefficient is 5%. The fractional bandwidth is about 5% for this design. And you can see the realized gain copol then in the E-plane, how this looks like. And it varies quite a bit also over frequency. So our aim is to see if we can increase the bandwidth. In fact, we want to double the bandwidth in this case. So what we do is we go and set a constraint on S11, be below minus 10 dB again, but in this case, starting from 19 to 21 gigahertz. And then at the same time, on the right-hand side, the model that we're going to use, we're actually going to oversize this dielectric because we want things to be cut away, right? So I'm oversizing this model, and this would result in a squint also in my far field. So you can see the cuts again here stretching from 19 to 21 gigahertz. So for that reason, we also put a constraint on the broadside pattern. So the realized gain to be above 3 dB. And I actually want to show a bit the UI in this way as well, that you can see how to define these type of KPIs. So essentially, this is how the GUI looks like. At the top, you select the coordinate system. In this case, I'm selecting Ludwig 3 system with linear polarization then and the component in the horizontal plane and for the realized gain, because again I want to take the input match into account as well. I don't just want to optimize on directivity, even though there's no losses in this model. So it's a bit different to the conductivity example. This is a loss-free model where we are sweeping from a dielectric constant of 1 to 20. So again, you want to push out those intermediate densities. Then you can also specify the angular range. So in this case, I'm taking in the phi equal to 0 plane or the E plane. I'm just taking a cut and I'm saying from minus 35 to plus 35 degrees in theta, I would like to have it above a certain level, which I'll show in a second. I can also, in addition, go and specify the frequency range and say, for example, I want to use the minimum value over the frequency range, but this will cause jumping between frequencies in terms of the objective function. So rather what I do is I say, look, let's take the center frequency and try to get that above 3 dB, and hopefully this pulls up the adjacent frequencies as well in terms of the patterns. Okay, then we go on and at the bottom we specify this to be above 3 dB essentially. Okay, and here you can see the topology that starts coming or that comes together. I don't have an animation here. It's a bit more tricky to see it like that. It's nicer to just see the strange surface that you have in the end. But I'm verifying this and I'm getting a lot more than 10% fractional bandwidth. But of course, the efficiency of the radiator will be degrading as I expand the frequency range. So I didn't plot excessively many cuts here, but at least from 19 to 21 gigahertz, you can see I'm fairly above 3 dB. At 19 gigahertz, maybe 2.7 dB, but again, it's not too bad. I can see the side lobe coming up. So one can put more masks on these when you're optimizing, but in the end, it's finding some very strange topology. And now whether this is you're able to print this or not, that's a different question, and how exactly you go about. Of course, we have also different constraints that you can set on the model. Symmetry constraints, manufacturing constraints can also be used. But again, these are just some toy examples to explain to you just the principles of this optimizer. And then ultra-wideband antennas, that's the obvious next question. We talked about multi-bands, integrated antennas, small antennas, volumetric antennas. What about ultra-wideband performance? So here, you can see a typical monopole with really wide band performance, just the inverted cone shape taken from Antenna Magus. Again, you can find the stuff in literature. So we're just saying, look, what if you take just the straightforward rectangular shape and you're positioning it above ground plane, coax feed again, and it's even shorted there, and you're saying, look, find me the topology of this thing by optimizing, again, the radiated power over this frequency. And you can see the topology coming together. Interesting enough is also at the bottom there, just going to go on to the topology. At the bottom, you can also see the sort of shape with the ground plane, what it's forming there, the sort of taper. And this is, of course, important to get a good impedance match over the entire frequency range. So, yeah. And you can see then your S11 on the right-hand side top being below essentially minus 10 dB from 1 to 10 gigahertz. So we're talking about a 10-to-1 bandwidth. And it looks fairly good, 86% radiation efficiency. Okay, there's this one peak at 2.5 gigahertz that one can still work on, but just to sort of show the principle. I said at the beginning I would circle back to circular shape optimization. So let's maybe look at this example again, and with this monopole, and we're even wrapping it around just the cylinder. You can start with topology optimization and you get your topology. But the point is, the next step is then to actually say that, okay, now I have something, some form. Can I shape this? Can I refine this to get better results out? And this is sort of the direction, or this is really the direction that we would like to take, that you can really have an end-to-end design, and not just starting with a black box and ending with some strange shape, but actually optimizing that shape and getting decent performance out. So this is things to come, things that you can already do today, but maybe in a more manual way. Yes, but in any case, there's a lot of stuff to explore with this, very exciting new technology. And so sort of in conclusion then, the topology optimizer is really a conceptual design tool. It's a great addition to Antenna Design Engineer's toolkit. I think everyone can make use of it and get some ideas for the spaces available for certain radiators, or using even existing radiators and seeing if you can improve a topology. Now, it is not exactly the generative design solution you might be hoping for or hoped for when you came to this talk, but it does allow exploring new and different design spaces, and really within various constraints and seeding conditions. So yeah, maybe just a small note also for those of you that have access to SIMULIA's unified licensing. This workflow is already available today to test, because of course you need CST Studio Suite as well as Tosca, but with the unified licensing, you make use of your sim units regardless of the tool you are running. And for more information on all of this, you can always go and visit the knowledge base and take a look at this QA that we have available on this topic. So thank you.